tonight it's my pleasure to announce Valentin Zagrebnov with the talk titled Comments on the Chernoff Estimate. You're welcome.
So thank you. And so I would like maybe to hit, is it possible? Yes, it is. Here is a menu of what I'm going to present. And as you see, this is a kind of reflections on the so-called Chernoff estimate. Since during this our conference, we heard about Chernoff and different circumstances and the different way of using this adjective as well. I shall explain soon what I mean by Chernoff estimate or Chernoff product formula. So the menu you see, and now I try to explain what it's about. My motivation to present this talk was the following. In fact, there are some news on this, what I shall call Chernoff estimate, but to motivate you, I simply to present what is general motivation of Chernoff estimate. The motivation comes from, in fact, from the Lee-Trotter-Kato product formula. So Lee is 1875, yes, 75, Trotter in 1959, and Kato is 1978. There are three steps in this direction, key steps in some sense. And Trotter product formula is a formula about convergence of this product, which is a product of couple of semigroups in the power n, and with conditions which are sufficient condition which are formulated just above. This is, let's say, essentially Trotter theorem. Lee, that's a statement about matrices, which is a particular case and the simplest case. Kato is a more sophisticated version of what is written as this product, but I would like to stick with the exponential version of this product formula. What it says that this product in strong operator topology in Hilbert space, I'll stick with Hilbert space, although there are things which can have or can be mentioned, but not obligatory on the Vanek space. That's much less transparent part of this activity. And to prove this convergence, this means this product formula, there are two philosophy, there are two strategy. One of the strategies is proof number one, which is telescopic method. Now on, I'm going to speak about not contraction semigroups, which is indicated here. And what is this telescopic method? It is simply to present this difference as a sum. And as you see that what you need to check and to control to prove convergence or what is on the left-hand side is in fact in red, just in the middle of this long sum. If you succeed to let's say carefully estimate this difference, which for the first glance clear should be smaller and smaller as soon as n tends to infinity, it is the key for the proof. Although here is the number of terms which is also proportional to n, so there is a kind of difficult and complicated problem then. Another way to do, so that I don't know, this. Another way to do the same, this means the proof, to work out the proof is called the Chernoff estimate, which comes back to 1968. What is this? Chernoff proposed a more general setting at certain moment. Although when I talked to him and he said that no, it is not very much what he had in mind. What is this? Let's look on this combination 5. This is product, in fact, and then we have to Trotter-Kato formula to prove the strong convergence. Then let's present this difference as two terms. One term is this product of power minus this special exponent, and then plus the rest, and with my notations, which is Cn equal this, what is indicated here. It is some kind of almost identical manipulation. So you see that now the problem of the proof of the Trotter formula split in two steps. One F, which I shall now on Chernoff estimate and Chernoff product formula. Chernoff estimate will be estimate of this norm in red. And the second one, this is different stuff and the different problem, which is in fact related to convergence of semigroups, which is known as Trotter-Kato convergence in strong topology, for example, here, strong operator topology, and comes back to 1959. So I stick, first of all, on this red part. What about this? Sorry, it's just opposite direction. Voilà. So what is about this red part? This red part is what I would like to explain how to estimate, and that's Chernoff who estimated this first time. And this estimation is called now on as square root of n lemma Chernoff lemma. In fact, you estimate this difference of powers using the following presentation. That's I simply cite quote Chernoff. You present it like sum, and then in this sum you estimate this difference between powers n and m of contractions f, and then you use first the following simple observation. Since it's contraction, then you can estimate it as a first inequality. Then you use again telescopic representation for this difference, and to arrive to this coefficient and difference in operator norm. So now we can do everything in operator norm. That we have contractions only. So then from this formula you get estimate of Chernoff estimate. In fact, that's what I promised to call Chernoff estimate as this difference and some in fact. Using Koshu-Bunyakovsky inequality, you can estimate the sum, and you reach to this estimate. That's a trivial Cauchy-Bunyakovsky presentation. And in fact, the sum is really coincide with the square root of n. By the way, I attract your attention that this is in fact weighted sum of squares, and this weight will play important role in my talk later. So you see that now you have estimate with square root of n, but in fact, as you see, this Chernoff estimate is a kind of strange estimate, because when for large n it doesn't improve accuracy of the estimate, just opposite, the upper bound in some sense that's increasing. So so far, let's look on the contractions F, which is phi, and this phi is a family. For example, strongly continuous family of operators which are contractions, and then we plug in these families inside in state of this F, and what happens that then you can write or rewrite this right-hand side, which was square root of n, now as t over square root of n. Why? Because you can divide this difference by the t divided by n. That's trivially. But now we reach a convergence. Why? Because by condition of the Chernoff theorem, this is nothing but, let's say, right strong derivative on the domain or the core of domain of generator C, which is presented like that. So you see, since on the core, it converges to 0, and the core is dense in Hilbert space, here you have something which controls the convergence to 0. And the rate of this convergence, the conditional rate, in some sense, because it is point-wise convergence, rate in each point is of the order 1 of square root of n. So in some sense, it is the end of the proof, because as I said, now you can extend this convergence for any x from Hilbert space, because the core is a dense subset in Hilbert space. What is new in some sense recently, this is, we in fact assisted this talk of Möbius and Roset and team. He explained on this conference that they use another version of Chernoff estimate, which fits better to into the when they study so-called Xenoproduct formula. I recall that Xenoproduct formula is also product formula, but I simply read on that. In Xenoproduct formula, instead of this factor, or instead of first factor, you simply put a projector. So that's a product formula which contains exponent, semigroup, and projector. This is called Xenoproduct formula. So for this Xenoproduct formula, they found with Steve and Roset that another version is better, and they produce some proof. I tried trying to understand the proof. I produced my proof, and then this my proof is I presented here. So what we do for the another version of the Chernoff estimate, we look on this difference. We present this telescopic way, and we start to estimate this difference. When you start to estimate a difference, you can expand exponent, because it is exponent of with the bounded generator. I recall you that F is a contraction, in fact, and you expand and you subtract. Here is F minus this exponent. What is rest? It is written here. And what then you get is the following: you plug in this identity in the place of this red difference, taking into account that F is contraction. You can do summation. You have n terms, because this is a sum comes from the first term, and then you sum also this one. But then this converges and converges in the sense that you can again take off this power cube, and this gives you exponent, which is again contraction operator, and you reach this estimate. What does this estimate say? That you remember that in the case of in the case of Chernoff, here it was square root. Now it is not square root, but n in the power 1. Although now you have here this difference in square. Now, if you produce the same, if you follow the same strategy, you look on the strong estimate, not operator norm, but strong estimate. You have here this square, and then you again divide it by t square and multiply, and you arrive, because of that, you arrive to the estimate, which is again now is of the order t square over n instead of t over square root of n, and that again gives you convergence to zero. So this is a way to establish a new version of Chernoff estimate in the strong sense in this way. Now about revision. So far so good, but you see that, as I said, we would like to improve this philosophy and the estimate of Chernoff. First of all, because the aim, as I indicated here, is the operator norm estimate. Everything before was heavily based, I mean the estimate and convergence, were heavily based on the fact that here you have this difference. And this difference, if you use correctly conditions of Chernoff theorem, give you finally the derivative or derivative of square of derivative or cube of derivative, and then you use that's, let's say, uniform boundaries principle to extend convergence on domain or on the core to the whole space. But if you would like to do this in operator norm, these kind of estimates are in some sense useless. What is then the idea? The idea was the following. Let's split this again, the sum, which represents the difference produced by Chernoff, in two parts. Central part, this means that when difference between m and n is smaller some epsilon n, and tails, which means m minus n is larger than some epsilon n. And then do the following. As I remember you that we already have seen this combination of exponent n in power m and m factorial for estimate which leads to square root of n. In fact, this is nothing but probability of Poisson random variable. So now I would like to use this to estimate the central part, not central, but the tails, because for tails it's a rare event from the point of view of Poisson random variables, and this Chebyshev inequality says that if you would like to estimate this probability of deviation of the random Poisson variable from expectation, it is less than variance divided by epsilon square with this epsilon square with this epsilon here. So if I rewrite this sum as two part, central part and tails part, then I started to treat these two different parts. First, tails. For tails, we have this sum, which is I rewrite, and this is indeed very frequent. And then I try to estimate this difference. Since it's a contraction operator, this is a trivially 2x because it's a norm of less than norm of each f in power mn. And then I have this one, but this one exactly the probability of deviation, which is in the Chebyshev inequality. So I use use this Chebyshev inequality to estimate the sum, and I reach to this probability sum of it. This is a variance. And this Chebyshev inequality gives me here this power n and divided by epsilon square, if you remember this one. This epsilon square, now this epsilon n square. So for the moment, this is the estimate of tails, and you for the central part, we look on this difference. We represent it again using telescopic procedure as a sum. This sum gives you, unfortunately, this factor if you would like to estimate at that stage. And finally, again, since it is contraction, you reach to this upper bound. So for the center part, you have estimate which still contains 1 minus contraction. Unfortunately, we did not, let's say, suppress this difference between this difference. So I call this epsilon n lemma, and this epsilon n lemma instead of square root of lemma. Square root lemma says that this Chernoff estimate now has the following form. This is nice because it is almost prepared for the operator norm estimate. But unfortunately, this is less nice because we would like to have something small, which is not absolutely clear because we don't know how to, for the moment, manipulate with this epsilon. Now we can simply optimize this estimate, varying epsilon n, and for the optimal value of epsilon n star, you reach, in fact, to so-called cube estimate, which has this particular form. You simply optimize this with respect to epsilon. So what is epsilon? In fact, epsilon tends to 0, epsilon n, with the rate which is 1 over cubic of n. That's what we reach from here. Unfortunately, what we get is again something very similar to original Chernoff estimate, but instead of square root of n, you have here this cubic root of n. That's the only what we gain for the moment, which is not very much what we want. In fact, as you see, still it is dependent on the although you can of course use the previous procedure and you reach to convergence now with the rate which is like that 1 over cube root of n. As you see, our most problem is this term, and this term comes, in fact, from this term, red. Now it is clear that you, at least it became clear that you have to impose more conditions on contraction, because for the moment it is a general contraction to control this difference. One of the way to do this is to look on so-called quasisectorial contractions. What are quasisectorial contractions? That's a contractions such that numerical range of them, these contractions, it belongs to a specific domain, which is I called d alpha, which is with a certain angle alpha. And I would like to maybe to show if I can. Yes, I can. I try to show this domain like that. Yes, that's so. In fact, domain for this numerical range of this quasi-sectorial contraction is in
Sorry for a small interruption. The time for question has started. You please can proceed, but then you will have less time for questions. Please proceed.
I would like to finish this statement and then maybe after. So you see that this is where it is. So angle is comes from the fact that it is a heritage of so-called sectorial generators. But as soon as you stick with this kind of contractions, you have a nice estimate. Namely, you remember that what we had in mind to estimate, it reduces to the following proposition. For this quasi-sectorial contraction, we have a property which Charles already mentioned. This is a kind of Rit operator property. Namely, the powers are such that you have this estimate 1 over n plus 1. So looking on what we had as a most problematic point is this difference. This difference now can be estimated using this property of quasi-sectorial contractions. And you see that now for the central part, you have this estimate. What you have as a conclusion? You have as a conclusion the following observation. Now estimate in the operator norm of this for f as a quasi-sectorial contractions. You split on the tails, center. For tails, you have Chebyshev inequality, and finally 1 over the 2n over epsilon square. But now for central part, you have this let's say rich type estimate with this rate of finally with this rate, and it is here. Now you optimize with epsilon with respect to epsilon, and you reach that epsilon star is this optimal value of epsilon. That this is a range of the central part. In fact, it grows as n in the power 2 over 3. So you see it is fine because these and these terms, they produce you this estimate. So in fact, this is the end of our problem with operator norm Chernoff estimate. It is solved in this sense. It is solved like that. What I would like to remark, that we are very far from optimal estimate for Chernoff. Why? For the Chernoff estimate. Why? Because if you look on the self-adjoint contractions, then with spectral representation, you can easily find 1 over n, which is much better than 1 over n 1/3. So, in fact, this is a dream and the aim of this activity to improve as much as possible these estimates. Why it is important? It is another problem. What I also have to yes. Yes. What I said? Oh, yes. So then at that moment I can stop because the essential part was explained, and the dream or for the future activity is also indicated. Thank you.